but as soon as it comes up, the normal force is not there anymore. So while the normal force is not zero, the displacement is. And as soon as the displacement is not zero, normal force is. The short of it in the end is the only thing doing any work is the conservative force. And therefore, I was hoping for unison at that moment. It would have been really cool. Tears of joy streaming down my face. If the only force doing any work is a conservative force, what must be true?
Energy is conserved.
Yep. And so we can just do a conservation of energy problem on this one. It's a whole lot simpler than doing F equals ma. Because frankly, there's torque involved, so then you have to do tau equals I alpha at the same time. And I'm just not ready to do that right now. And so we got initial kinetic plus initial potential equals final kinetic plus final potential. Now this whole thing about the kinetic. I'm going to explain it one way and then I'm going to justify it after the fact. I'm going to treat this as we have this object that's rotating. So I have this rotational kinetics, but I also have the ball moving down the ramp. It's not just spinning in one place. And so I have this linear kinetic or translational kinetic plus u sub I equals k final, k rotational final plus k linear final plus u final. Actually, we need more specific use of g. So I'm going to treat the two energies, the energy dealing with rotation and the energy dealing with the whole thing moving, as separate entities right now. I will justify that after we finish this. Here it comes. What's the formula for linear kinetic energy? It was so quiet for all of you speaking at once. It did sound like a single voice, though.
We just got really good at it.
Yeah, I'm impressed. But more confidence this time. Let's try it again, except this time, like you mean it. What's the formula for linear kinetic energy?
1/2 mv squared.
Oh, let's try this one more time. This is just for me. You just start out with 1/2 mv squared. You don't throw any of the extra stuff in there. What's the formula for kinetic energy?
1/2 mv squared.
I'm not sure that many points on enthusiasm, but you had synchronicity, so I'll take it. 1/2 mv initial squared. What about rotational kinetic? Not looking for unison, just want somebody to say it.
One-half I omega squared.
Yeah, hey, written right there. The formula for potential energy related to weight.
Has a G and it has an H.
You said you asked if it has a G in it?
I know it has a G and it has an H, but I know there's like a third one. I don't remember what it was.
Is it MGH?
That's the one. Equals 1/2 I omega final squared plus 1/2 mv final squared plus mgh final. So we're just dealing with whatever energy we have to start with, we have the same at the end. Now, what can we get rid of? Okay, what do you want to get rid of?
Final one?
Okay. And we will blame it on Amy. All right. Amy says the final height is 0.
The initial velocities.
I guess I didn't say that, it starts at rest, so it just starts at rest. Can't get rid of anything else?
The mass?
Not yet. Because this term right here, these terms don't have mass explicitly in it yet. But we're gonna change that in a moment. What's the other thing that we can make 0?
The final velocity?
No, I hope not.
Oh, no.
It's not hitting anything at the bottom. We just stopped carrying at that point.
The initial angular velocity?
Yes, it starts at rest. It's not spinning in place. Waiting for you to pop the clutch.
That's what I meant to say.
Okay, yeah, sorry, I misunderstood.
Yeah.
Alright. So now we're left, we went from 6 terms down to 3 terms. It does look simpler, and so let's rewrite what we have there and see what next to make it simpler, because Amy still wants to get rid of mass, and we do not want to disappoint. So mgh initial equals 1/2 I omega final squared plus 1/2 mv final squared.
Now you get rid of it.
We have a formula for I because I said it verbally, solid ball.
2/5, whatever it was.
Yeah, 2/5, whatever it was. So we have mgh initial is equal to 1/2 2/5 mr squared omega final squared plus 1/2 mv final squared. Now we have mass in every term. And even though I drew my m slightly differently, they are all the same mass. So now I'm down to ghi is equal to, well, that's 1/5 r squared omega final squared plus 1/2 vf squared. And we can do one other simplification. It was written on the board over here, but it comes down to the relationship between linear speed and angular speed. And what is that relationship? I know all of you, I can read your minds, and all of you are saying it, screaming it out loud in your heads. Here to here.
Omega equals VR, or angular speed is equal to linear velocity times radius.
Ooh. You got all the letters, the order you got mixed up.
omega equals VR?
No.
V equals omega R.
That's the one, V equals omega R. If there's no slipping, V equal to omega R. If it is slipping, then, well, I should say, the speed of the center of the ball is equal to the angular velocity, angular speed of the ball times the radius of the ball, if it's not slipping. And so this right here, hey, we just happen to have R squared times omega squared, that's just V squared. So this becomes GHI is equal to 1/5 V final squared plus 1/2 V final squared. So GHI is equal to 7/10 V final squared. And so my VF squared is equal to 10/7 GHI. And so VF is the square root of 10/7 GHI. If there were no friction, it would be the square root of 2 times G times H sub I. So the linear speed is less because it's rolling. You can think about it this way, that if there's no friction at all the energy, all that potential energy gets converted into the linear kinetic, the kinetic energy just to make it go. Now that energy, you start out with the same amount of potential energy, but now it gets split. It gets split between the rolling and the actual moving of it down, going down into the rotational and the linear piece. So there's less energy left over just to have it go down the ramp. So if I said this was a 15-meter ramp, angle of 30 degrees, Earth, then this becomes 10/7, square root of 10/7 times 9.8 times the initial height, which is 15 times the sine of 30 degrees. So we're around 10. Seems like a little bit more than 10, but 10.205. Units?
Meters per second.
Isn't it glorious? One might even be so bold as to say it's magniflorious.
Where did the 15 sine 30 come from?
The
Oh, is
fif-
that
oh.
just the angle?
Yeah, I gave an angle of 30 degrees and hypotenuse of 15 meters.
Oh, I didn't see you get the angle, okay.
Yeah, I was in ninja mode. You missed it. Any other questions? All right. Let me justify this step right here. When I did the kinetic energy into these two pieces. Oh, actually, I gotta do one other thing first. Let's take a break, stretch your legs, take a 5-minute break or so. Come back, we'll talk about parallel axis theorem, and then we'll get into my justification for this. And I'm gonna take the bold step of pausing this, hoping to remember to turn it back on. That sounds either sweet or frightening, I'm not sure which.
Well, in our respective areas.
Okay.
You grade us on our effectiveness.
That was gonna be interesting, I just paused it right before I said that's either sweet or disturbing, and I'm gonna let them figure out what we're talking about. All right, I have here two sticks. We will call them sticks. They have the exact same mass, but there's a difference between them. Obviously, this one's much easier to spin back and forth than this was. It's not an issue with the fact that my right hand is just so much stronger than my left hand, not the case, because I can switch it. And this one's still much easier than this one is. Why? You need to see the sticks, I'll be glad to bring them over to you.
Is one feet. You said that they're both the same mass?
Yes, they are. Same mass, same length.
Are they the same weight?
Yeah, same weight as well. If you wanna.
Is one hollow?
Well, they both have the exact same hollowness.
Just cause, yeah, physics.
What's the difference between them?
One's much heavier.
No, but they're the same weight. Hold them this way. They weigh about the same.
I wanna go on the line and say the center of mass.
Center mass is in the middle, both cases.
Do they both have the same holes in them?
Same, it depends on what you
Whatever
mean by
you're-
that. I could legitimately say yes, but I think that might be misleading. I don't know. I mean, physically, I mean, to your Brandon, physically, is there a difference? Look at the ends there. Is there a difference between the two?
Yes.
What's the difference?
One you can see through, the other you cannot.
One's blue and one's red.
Oh, yeah, well, that's that too. As everyone knows, the blue is harder to turn.
When I said holes, that's what I mean, like in the middle, are they like the same? Okay, can you see through the middle of the same?
Should be able to see through the middle of this one, and then the outer ends over here.
And you cannot for the red one, right?
The red one, these are blocked.
They're solid.
Yeah.
Is the weight in them distributed differently?
Say it again?
Is like the weight inside of them distributed differently?
I'm missing a key word there, sorry.
The weight distribution is different.
Yeah.
Yes. I assume that's what you,
That's what she was saying.
yes. The weight distribution is different. The weight is the same, but in this case, in the red case, the weight is concentrated around the center. In the blue case, it's concentrated on the outsides. So, it's connected to what we were just doing there. Why is this one harder to turn?
The weight's on the outer edges
Keep going.
as opposed to the middle.
Yes, absolutely true. You wanna?
What?
Sorry, I don't want to, if you're on a roll, keep going, or
I don't know, the weight is acting on the edges more than the center.
Let's relate it back to physics. Yeah, but what you're saying is absolutely right, and that is key, but, I want to bring in some of the language we've just been doing. Say it again? If I'm holding it like this, the axis of rotation is pretty much in the center of both of them. When Amy first grabbed it, she had the axis of rotation down here. Why does distribution of mass matter?
There's more area for the weight to be distributed.
Yeah, that's a hard path to go down to get to the right answer, so.
I'm spitting something at you.
What was the last thing?
I said I'm spitting something at you.
No, I appreciate that. I'm hoping either it'll click and you'll say it beautifully, or it'll click with someone else and they'll pick up where you've left off.
Does it have to do where you hold it?
I think that pretty much this one's still gonna be harder to spin no matter where I'm holding it. How hard it is to spin will depend upon where I hold it, but this one's still gonna be more difficult no matter where I'm holding. All right, what were we just talking about?
Rotational kinetic energy?
And before that?
Are you talking about before the ball and ramp, or?
Yes, before ball and ramp.
Would it have to do something with the axis? With the axis?
Trying to think of which, yeah, it's something to do with axis. It's,
The door. Are we talking about the door or before that as well?
no, we started with the door.
Yep.
We were deriving the kinetic energy.
Mhm.
And in the course of doing that, we derived, I'm sorry, spoiler, moment of inertia. That's what we're talking about here. It's the sum of all the little MR squareds. So I have these two objects here with the same mass, except because the mass is distributed farther from the center. Recognize the import here. R is squared. It's going to have a much more dramatic effect than the mass will. So if I put the mass farther away from the center, I will have a dramatically larger moment of inertia, also known as rotational inertia. It's harder to get it moving. Think of what the law of inertia is. Object at rest wants to stay at rest. Object in motion wants to stay in motion at a constant velocity. Object at rest wants to stay at rest. Object rotating wants to keep rotating. The greater the moment of inertia, the harder it is to move. So this one with the mass out here, it's harder to get moving, but once it's moving, it's harder to stop. And I definitely feel it when I try to go back the other direction. I'll just do it that way so my thumb's not taking all of it. And this one, because the mass is right there at my hand, I can zip this back and forth easily. And then relating to the axes. Recognize the formula I gave you for the solid cylinder rotating about its center was 2/5 mr squared. However, what if it's not rotating about its center? So if I have a ball like this, if I rotate it about its center, moment of inertia 2/5 mr squared, or we have some radius and some mass. But if my ball is rotating about the endpoint here, moment of inertia, same, bigger, smaller. Those are your three choices. I guess non-existent, but I'll just go ahead and eliminate that.
Unless it's bigger.
Why?
Because when you have it spinning right down the middle, the radius is the radius of the ball, but on the end, it's gonna be double that, because it's not down the center anymore. It's also gonna be terribly unbalanced, but.
Yeah. So because I have mass farther away, exactly what Ian was saying, because I now have mass, that used to be the the farthest mass was just the radius away. Now the farthest mass is two radio away, or as you could say today, a diameter away. And because the more mass there is farther from the axis, the harder it is to rotate, the greater the moment of inertia, or rotational inertia. So how do you deal with that? Do you now need to have a whole slew of formulas for every position of this? No. The parallel axis theorem. Apparently with a fading marker. So if I have an axis that is parallel to an axis where I know the formula. So I know the formula when it's spinning about here. This is parallel to that, thus the parallel axis theorem. Says that the moment of inertia about the new axis, which I'll call T, is equal to the moment of inertia about the center of mass plus mh squared. Unfortunately, the derivation requires calculus, and so not worth the having to change it into non-calculus, because that would be probably an hour of your life you won't do that. So what this means is, if I shift my axis from the center of mass, I just use this formula, and I have what the axis, and I have what the moment of inertia is. So in this case right here, I have the moment of inertia about that axis is going to be what it is around the center of mass, so 2/5, and again, solid sphere. 2/5 mr squared plus the mass times h. H is the distance from the center of mass or to where the new axis is. That distance right there is h. So in this case right here, h would be the distance from the center of mass to the edge, and it's h, which is just the radius of the ball. And so rotating about the edge like this, the moment of inertia is 7/5 mr squared. The moment of inertia is 3.5 times more. That's your textbook. Do it. That's your textbook does. Okay. Let's apply it to a case that's actually on page 330. They give you the moment of inertia of a thin rod rotating about its center. A rod of length L, mass M. And so if I have this rod rotating about its center there, this is the thin rod. The moment of inertia is 1/12 ml squared. And so what I want us to do is, what is the moment of inertia of my thin rod rotating about the end? This will work. So thin rod rotating about its center versus rotating about the end. Well, I'm moving the axis that far. So the moment of inertia will be the one about the center, the 1/12 ml squared plus m times, well, how far did I move my axis?
Half of L.
this becomes 1/12 ml squared plus 1/4 ml squared. And 1/12 plus 1/4 is 1/3. And on page 330, they have this case right here, and they write ml squared over 12, and then right beside it to the right, they have this case right here, and they have ml squared over 3. Some textbooks will not give you the second one just because using parallel axis theorem is easy enough to do it. All right, questions to here?
Where did the 1/4 come from on that?
Because we moved the axis half the length,
Yeah,
so that's why we have 1/2 L here,
right.
and that 1/2 L is squared.
Oh, okay,
So that 1/2 squared gets you that.
okay, yeah.
To the landfill you go. Alright, so you're good?
Yeah.
Alright, other questions? Alright, so at various times, and I hadn't done this yet, at various times, I'm gonna make reference to the Rube-Goldberg test. If you look under course documents, old tests, or maybe old tests is a separate category by itself. I really should standardize it across all my classes. There's, eventually you go down there and there's this, under one of the test 3s that says Rube-Goldberg test. And I think for one of the classes, I can't remember which one, there's even an arrow pointing towards it saying this is the one. The Rube-Goldberg test basically was as close to a one question test I've ever done. And it had parts A through P. So that, but it's still one of my favorite tests. I can't say it was the student favorite, but it was one of my favorite tests. That the whole thing flowed. So basically, if you got the last answer correct, then I knew you had done there's one part that could have been done separately, but you had done all but that one part correctly, if you had the right answer at the end. Or you got really lucky. Which does happen, where a couple of mistakes cancel each other out. So, at this point, there's collision problems in it, and then there's some conservation of energy in it, there's something rolling down a ramp, which we just did. So there are parts of the Rube-Goldberg test that you can do now.